So our speaker now is Harshita Gandhi. Okay. You have 15 minutes and 5 minutes for questions.
Thanks. Hi everyone, I'm Harshita. I'm a second year PhD student in Aberystwyth University in Wales. Right. Okay. So I'm working with Professor Hugh Morgan, and this work was done in collaboration with Vaibhav Pant and Dipankar Banerjee because I started this work just before my PhD and I continued it during my PhD as well. The title of this talk seems quite long, no surprise, but I have tried to sum up in few words, which is how do CMEs behave? And I want you to look at this talk in a very general way to understand how kinematics of CMEs change when you try to find their 3D properties. Right. So I'm not going to go into much depth of introduction to CMEs because we had quite interesting talks yesterday. But a quick few facts about CMEs. On the right side, you can see a coronagraph image, which is showing a halo CME. A halo CME can be directed towards Earth or away from Earth. A couple of facts about CMEs. As you know, that CMEs originate from the surface of the sun. They have source region, and you can see them in the corona, in the coronagraph field of view. Oops, right. They were first detected on 14 December 1970 by a spacecraft called OSO. These are the couple of points which are really important, which is the kinematic properties of CMEs, because this is what I'm going to focus on during my talk. Right here I show speed and width ranges. So I write here 2D because since these coronagraph images are 2D images, and so far the catalogs that we have, they cover their 2D properties and not their 3D properties. So from now onwards, I will refer 3D as a true parameters and 2D as projected parameters. And this last point is quite important because we all are doing space weather forecasting. We use CMEs in some ways, and people doing CME arrival time studies, they know that CMEs can arrive between 1 to 4 days depending on the speed of the CMEs and their size as well. Right. Why study CMEs? So we know that CMEs cause space weather, and space weather cause geomagnetic storms, and which in turn causes disruption in our power grids and modern technology. So forecasting space weather needs better understanding of CMEs. That's why we need to study CMEs. And not just study CMEs, but study their true kinematics. Right here, I show a few lines about the geomagnetic storm that happened in Quebec. And this is what we want to avoid. That's why people are doing space weather forecasting. Right. Now, how do we study CMEs? We study CMEs through loads of spacecrafts, which are ground-based and space-based spacecrafts. We have SOHO, which was launched in 1995, and we still have data coming from SOHO. Right, so to study CMEs, we have coronagraph images. We get those from these spacecrafts, whether they are ground-based or space-based. And once we have these images, there are methods that have been developed to find their kinematic properties. Because as you have seen, that CMEs are these fast eruptions from the sun, and studying how their kinematic properties change can help us in better understanding their arrival time predictions at Earth. I will come back to this 2D catalogs later because I have compared my results with the 2D parameters that have been noted in these catalogs. Right. Now, this is the central research problem, not specific research problem in my case, but a central research problem in case of CMEs, which is how to reduce or remove projection effects, or in a better way, how to better understand the kinematics of CMEs. Right here, I show same CME, but from 3 different viewpoints. As you can see, this is SOHO-LASCO. So SOHO is a spacecraft, and LASCO is the coronagraph, right, this one. And this observes the sun from the Earth point of view, whereas the other 2 spacecrafts look at the same CME from different angles so that you have a different viewpoint of CMEs. And you can see that CMEs look different in appearance in all these three images. Right. Motivation behind this work now. So I'm highlighting just two main limitations, which is first, we have single viewpoint detection of CMEs, which lead to projection effects. We know that. Since we have these detections, we have got many catalogs which include projected 2D parameters. There have been improvements made to cover these limitations, which is there have been 3D detection tools and tracking done already, but and they have also improved the CME properties, basically the true and true 3D speed and width properties of CMEs. But they still lack a large statistics study, and that is where my study comes in. So key points to remember before I show my results. CMEs are observed in coronagraph images. We detect them, we track them, but so far it has been done in plane of sky measurements, and we have like loads of information about plane of sky speeds and width. Right. So main questions are, is there a need to remove projection effects in CMEs? We know that, yes, we know the answer. How do we remove projection effects? We know the answer to that. We have got multi-viewpoint observations. People are doing 3D detection methods to remove these projection effects. But the important question here is, do we see a significant difference after correcting projection effects? There have been papers which show that there is a significant difference, which is supposed to be, but my study is takes into account much larger statistics to see these projection effects more clearly. So this is where my work contributes. So some highlights here. This is a first large statistical study of CME true kinematic parameters. We have taken into account 360 CMEs. They range from 30 degrees to 360 degrees in width. Again, I'm talking about projected width. And it covers the solar cycle 24, so covers different phases of solar cycle. Right here, what we did is we wanted to see the imprints of source regions as well, not just look at the overall speed and width distribution of CMEs. So we divided these CMEs into their respective source region based CMEs. After that, once we had those, we applied few techniques on fitting the CMEs and to get the 3D properties of CMEs and compare them with the 2D ones. Right. So this is the data source and data selection criteria that we did. Right here, so basically I didn't fit the 360 CMEs because it would take ages to do that. But as you can see, there are few catalogs, CME KinCat and CME database, which is maintained by Institute of Astrophysics in Gyeongshin. They did the study for the first time, but I have not taken into account all the CMEs because a specific criteria has been employed to make sure that we have the consistency in the CMEs if I'm taking CME events from different catalogs. Then there are a few more CMEs from different papers, but to just to make sure that I have done fitting on 34 CMEs during this study. Right. So the methodology employed in this work was first to create a data set, a large data set. We had CMEs, but like I said, there are 100 CMEs in some catalog, 50 in some other else. So we wanted to make sure we have a consistency in selection criteria, and we create a catalog of 360 CMEs. After that, we segregated them on basis of different source region, and we found that out of 360, we had 170 belonging to AR, which is active region CMEs, 100 prominence eruption CMEs, and 90 from active prominence CMEs. And right here, we did 3D reconstruction on 34 CMEs during this work. This is a screenshot of a GCS reconstruction. After you do that, you get some best fit GCS parameters. I'm not going to go into depth of how you do GCS fitting. You can find the Python code and ideal code online, or you can refer to this paper right here. After you get the best fitting parameters, you can see that we have a table of date, time, source region, latitude, longitude, tilt, aspect ratio, half angle. So these are the model fitting parameters that we get after fitting CMEs. After that, we find speed and width like everyone else has done because we are trying to maintain a consistency in our data set. Just to find the estimation of error in speed, we used a technique called bootstrap. Bootstrap works in a way that it resamples your data so that you don't have to repeat the experiment. There are a couple of procedures in IDEAL that you can use. What we did is we used something called boot XY fit, which does a linear fitting on your height time data points. So you can provide how many repetitions do you want to do with your sample, and it gives you a speed distribution right here. From the speed distribution, we found the 1 sigma uncertainty, and the uncertainty in the speed, in the height time plot is shown in the shaded area. So that was quite helpful because we compared the bootstrap speed with the linear fitting speed, and it was under the uncertainty error bar. And after that, we compared the 3D speed with 2D speed. So this is the final table that we got for, so right here I'm showing the table for just 20 events out of 34 that I did the fitting on, but we have got the whole catalog comprising of 360 CMEs. And this is what we have, the source region, and you can see the rest of the columns. We also have their 2D speeds and width cataloged in the table as well. Right, so coming to the results. Right on the top, you see 2 plots, and these are speed distributions. So for now, I would say to focus on these 2, as these are the 3D speed distribution plots. This one right here shows a distribution of speed. It is not symmetric. It is rightly skewed, as is this one. But you can see that the high-speed tail of the distribution is significantly boosted up to 2,800 kilometers per second, whereas low-speed tail of the distribution is suppressed in terms of number of CMEs. You can see a significant difference in when you do a after correction speed distribution and comparing it with the 2D speeds right here. To see their imprints of source region, we further distributed this, split this distribution into 3 distributions, and we're overplotting it right here. As you can see, the dark black one is the distribution coming from AR CMEs, and it's mostly rightly skewed. You can see the high-speed CMEs coming from active regions, and then after that you've got AP CMEs, and then you have got prominence eruption CMEs, which we know already that prominence eruption CMEs are not that fast as compared to active region and active prominences. And just to compare it, with the 2D properties, you could see the average values right here. So, I mean, I wouldn't say that, but you could see it right here. You can compare them. As you can see, the average 3D speeds are much higher than the average 2D speeds. Right. This is the distribution of comparing width of 3D and 2D. You can see, again, that there is a significant difference in the width distribution. The average width before correction was 112 degrees, whereas this one was 77 degrees. We know that apparent angular width in plane of sky tends to be wider than the true width, and we can see it here. So we can clearly see huge amount of projection effects in the distribution of speed and widths. Again, we split it into source region-based CMEs, and again, you can see that the AR and PE CMEs, AR and AP CMEs have got high width as compared to the PE CMEs, which is 66 degrees. And still, there is a significant difference before and after correction. Right. This is an important result as we compared the CME true speed with CME true width. This work has been done a lot, but with 2D parameters, as you can see on the left. So we just wanted to compare our result with the 2D speed. So one thing that we found is wider CMEs tend to have higher speeds, and the slope varies with a factor of 5, almost 2.5 times the slope of the, in case of 2D parameters. When you split this into source region, we found an interesting result that for 170 AR CMEs, the slope is 7.22, and it contributes more in an overall speed width distribution. What we found interesting was the relation between true speed and true width coming from PE CMEs, which is prominence eruption CMEs. We found a positive correlation in the 2D plot, whereas a negative correlation in a 3D plot. What I think can be because of a bias include in the parameters of the prominence eruption-based CMEs, but we still need to revisit the prominence eruption plot again. Right here, we show different parameters and their correlation coefficients. This is the final result, final plot of the study, which compares the true speed in the outer corona with the projected speeds. Not many papers have this plot. I guess 2 or 3 papers have got this plot, but with 50 or 60 events. We can see that true speed varies by a factor of 1.3. The red and blue data points correspond to the projected speed from stereo and from LASCO point of view. We just wanted to see if there is a difference in the slope, but we don't see much difference in the value of slope. Right. So this is the summary and conclusions. This is the final table, and comparing different CME properties for all 360 CMEs, for AR CMEs, AP, and PE CMEs, with the correlation coefficients. So a couple of things to note here is that we found this true speed varies by a factor of 1.3. Of course, there is uncertainty in it. 2D speeds are underestimated by approximately 30%. Few papers have shown the exact numbers, but few papers show that it's underestimated by 20%. Compared to other statistical studies, these findings aim to fill the gap between true and projected parameters of CMEs. And again, we present a large catalog of 360 CMEs. Obviously, it has got a selection criteria, so you can use it if your aim fits that selection criteria. Right, so this is the future work and ideas, and probably my last slide, yes. I compare my current work, and it can be related to other topics as well. So for example, you can use the 3D properties of CMEs as an input to solar wind models to improve those models. You can use it to find a geo-effectiveness of CMEs. So for example, in my catalog, I have got 60 halo CMEs coming from active region, and you have got 3D properties of those CMEs as well. You could further do a CME and source region connection study, depending on this work. You can investigate, so there are papers by Tomic et al., where they look at the decay index in the active region, and they see that how that decay index changes when a CME erupts from the active region. So that is something that I want to look in the future. You can also create a CME ICME catalog, again, with the 3D properties and not with the 2D properties. Yes. So this barcode gives you the poster. I actually made the poster as well. So if you want to look at it, you can. Thank you. I'll take questions.
Thank you. Do we have any questions? Yes.
Thank you for your very nice talk. I was wondering, how do you determine the source region of the CMEs?
Right. So to find the source region of CMEs, we used the AIA images and the EUVI images in stereo. Since we are doing a multi-viewpoint study, we use JHelioViewer to look at the disk of the sun and kind of back projecting it and looking at the post-CME eruptive signatures. If you've got coronal loops somewhere, you can easily find active region CMEs. It's not really difficult. But sometimes with the prominence eruption CMEs, it can be tricky, and with AP CMEs as well. So active prominence CMEs are the CMEs in which one of the foot points of your prominence is close to the active region. Not many studies have been done including those source region, but we actually saw in our work that AP CMEs tend to have higher speed as compared to even active region CMEs. So, yeah.
But so you did it like visually identified?
Yes.
Okay. Okay, thanks.
Yeah.
Any more questions? Yeah, in the back.
Thank you, nice talk. I'm a bit of not an expert on the field, but I was wondering about the fit that you showed before. What kind of fit are you using? Like just a least square, or you're using something more sophisticated?
The fitting method?
To find the correlation in the plot after.
Right, so the fitting is just a linear fitting.
Okay.
to find the correlation coefficient between the two
You didn't
parameters.
explore other methods?
No. So the thing is that we just wanted to do the study to see how 3D properties change and to compare them with the past studies and to just, I mean, I'm still exploring the other statistical methods to apply, because you can see a huge amount of scatter in these plots. So fitting something where there is no higher positive correlation doesn't make sense.
Yeah.
But like I've said, I wanted to compare my results with the past studies and to see where it stands.
And I was actually wondering if you measure the distance between the velocity and if you see that the scatter increases with the CME through width. So like here you're plotting the two quantity, but you can actually plot the difference with the fit, so to measure how the scattering increases with the intensity.
Right, okay, I'll look into that, yeah, thank you. Thanks.
Okay, I have a question myself. Because recently we did into this business of 3D reconstructions, and I think you're overconfident about your 3D true speeds, because different observers have different fits and they fit different structures.
Yes.
So be careful about it, because you didn't do any errors on your fitting. You didn't do it multiple times by multiple observers.
No.
Okay,
Yeah,
you
I
will
know
get
that.
a great
Yes,
error bars
yeah,
there.
it brings bias
So-
to that.
So keep in mind about that, and you also combined your 360 catalog by various other people fitting.
Yes.
So there is some scatter could be due to the
Exactly,
different
but when we
observers.
made sure that we have bright CME features in all those. So I personally checked all the videos, movies of the CMEs for all 360 events, and obviously their selection criteria is mentioned in their research papers as well. But yeah, I totally agree with that.
Okay, you're aware of that. So just to highlight or about our recent results, so 3D reconstruction is not the answer about geo-effective CME, geo-effective CME. Keep in mind you need other parameters than 3D deprojection by itself. So this is a very important point. And I would like to, it's an open question for the audience, if you can make up a machine learning thing that you can get the observer out of the loop, because this is really so subjective about the 3D fitting. If you can really apply some method that do it completely automatically by following some routine, of course, minimal error bars. So this is important in our studies because the observer is putting a lot of error in these fitting procedures. Just a comment.
Yes.
It's not
okay.
it's not
Thank you.
There is a recent paper that I think the first author is Christine Verbeek, that they estimate the error of the GCS fitting. So they did this study performing different people were fitting the same CMEs with the GCS parameters, so they have an estimation of the error, which is very nice because you can also include the errors in your...
Yeah, exactly, but I'll have to make sure that those are the same events.
Yes,
But
of course.
Yeah, thanks.
All right, thank you very much.